So I think everyone here knows about Bacalhau a little bit. We've been working on it since February. I wanted to let you in on a secret. This is our master plan. It's not actually a secret. Please tweet it. Everything we do is open and public. So, essentially, we are doing two things. The first thing is to build a volunteer network that scales. So what we want to do is to learn how to make it scale and how to make the user experience amazing, so that we get lots of users and we build a big network and we test the limits of like how we're using libp2p and things like that, and make something that can run on hundreds of thousands of nodes globally with global speed of light latencies, and process loads of data and so on. We want to integrate it with tools that folks already use. So for example, Enrico's going to give a talk. Is Enrico in the room? He will be soon, hopefully. Enrico's going to talk about how we've prototyped an integration with Airflow. And we also want to find a bridge to having service providers who are currently running Filecoin nodes be successful in being able to also run Bacalhau on their nodes. And in order to do that, we need some kind of incentive mechanism, and we've got some ideas about how to kind of bridge to an incentive mechanism using FIL+. And Kai's going to talk about that up next. So that's the volunteer compute network, right? We want a volunteer compute network at scale with great user experience. The other thing that we want to do is to build an incentive mechanism for compute. Ultimately, what we are trying to do here is make it so that people can build incentive layers for compute on top of the work we've done for the volunteer compute network. So the idea with the mechanism is a protocol and some library code. The goal is that many groups should be able to spin off from this code base, from this library, spin off tokens, networks of different flavors, things that are in different places in Juan's triangle or whatever. And we want many groups to be able to be successful using this. So that's the context. So now for the rest of my bit of this talk, I just want to talk about, well, what's in the ... There's kind of going to be a gap between these two things, and kind of how do we manage that? So another way to think about these two pieces are in kind of two separate paths that we are going to tread concurrently. So on the volunteer network, we need great user experience, we need scale and performance, we need pipelines, for example, as a way of integrating with tools that users already use. We need to get lots of user adoption. Like I said, we need to find that bridge to getting service providers on board. We also need a story around encryption, how people can use private data in the network. I would say everything in yellow is fairly well understood. It's not going to be easy, but it's also not going to be that difficult. It's mostly just a matter of execution. Whereas all the stuff on the right is much harder and more complicated, and there are some open research topics in there. So in terms of the incentive layer, we're working on determinism, and in particular using WASM and the work that Simon's been doing. Simon will talk about his work on WASM to make it possible to have the users define jobs that always run the same every time you run them. Then we're going to work on the protocol, which is another way of saying kind of the rules of the game. We're going to work on interfacing with an accounting system or accounting systems such as smart contracts. We're going to work on formal verification, which is like a way to mathematically prove certain properties about the protocol. We're trying to learn about game theory, and how we can use that to also kind of understand behavior of the protocol, and we're also looking at reputation, and I'll talk about why there's a question mark on that. I also wanted to point out that there are some tensions between these things that we want to do for the volunteer network and things that we're going to need to do to make it Byzantine fault tolerant, basically. And it's like a tug of war, right, between these two things. We want a great user experience. Well, the best possible user experience is that anyone can rock up with a Docker image and run any code that they like, with threads and reading from dev random and GPUs with stochastic rounding in the hardware and all of this stuff. But we also want determinism, and that kind of pulls in the opposite direction. Because when you run things inside WASM, with determinism, you need them to be single-threaded. It's hard to use GPUs. You can't have random numbers, things like that. And another way that things are in tension with each other is that on the scale and performance side, it's easier to make a network that operates at great scale if you don't need to handle money, basically. Whereas as soon as you introduce a smart contract and kind of verification protocols, then yeah, you end up, unless you're careful, you might end up sacrificing some performance. But there are some interesting ways to work around that with things like payment channels. So anyway, these things will kind of pull against each other in some cases. So to kind of borrow from Dave's talk, like my take on our big, hairy, audacious goal is, like, together let's create the protocol, the mechanism, the rules of the system under which you can have a distributed compute network that could power the world's compute for the next century. Why not? That's our audacious goal. So then we're lucky to have, some folks from the team coming up to do talks and demos. We're going to have a demo on the FIL Plus stuff, the pipeline stuff, and the WASM and determinism thing. But before we do that, I've got some more words. So I'll just kind of go into a little bit more detail on each of those points, basically. So in terms of the volunteer network, we want great user experience. Now, there's just a lot of basic kind of blocking and tackling stuff that we need to do to improve the user experience of Bacalhau today. If you've tried to use it, you might have found that, like, sometimes your jobs end up in job state unknown. And that actually, and like when you run Bacalhau describe on them, you get job state is the empty dictionary. And what that actually means is that the job, no one has bid on the job yet. But that could be because there isn't any available capacity on the network for GPUs or something. So improving the user experience and surfacing that information back to the user, telling them that the input CID for your data isn't actually available on the network, and that's why your job is hanging, for example, is another example of that. There's some bigger projects as well, like when the compute node is downloading something from IPFS, why not give them an update on the progress of that download and how fast it's going and give them an ETA? When you're looking at standard out coming out of the job, it would be great if we could stream those logs back to the user rather than only showing you the logs right at the end of the thing, because it might never terminate, and then you never get to see what went on. We need to make the network stable and fast, and we're getting there. It's improving incrementally. I also have some UX things that Simon and I talked about, some ideas from Simon. It would be really nice to be able to run language workloads without the user having to Dockerize them. So just like, here's my Python script and my requirements.txt. Go figure it out. It would be even better if the system could automatically WASMify that Python script if it can. But if the dependencies that the Python script has are like PyTorch, and PyTorch doesn't run in WASM yet, then we'd fall back to running it on the Docker executor, for example. So that would be pretty nice. We've also got a ton of work to do on scale and performance. So we've tested the network up to 1,000 nodes on 4 big, beefy servers that are running on the same LAN with low latency between them. And we've done a bunch of work to get things stable at 1,000 nodes on 4 physical servers. But things get harder as soon as you geographically distribute them. And if you look at our current production network, for example, there's 3 CPU nodes, 3 GPU nodes. It's quite small still at the moment. there's 3 CPU nodes in Google Cloud in the US, and then we've got the GPU nodes distributed across the US, Europe, and there's one in my office in Bristol, in England. And they've all quite happily joined up and formed this mesh over libp2p, which is great. But then when we start adding more nodes across the world, then we start seeing network latencies going up quite a lot. And I think one of the reasons for that is that we don't have in the way that we're configuring libp2p, there's basically work that we need to do here to test and experiment on that. But I think we need to switch to kind of having a network backbone that's mostly in the same continent, and then have other nodes that join the network peer with that backbone so that we don't end up with messages hopping across the Atlantic multiple times in order to get stuff done. So that's work to do. We also want to support pipelines. I won't steal Enrico's thunder. I'm just going to let him talk about that when he gets to that. And then on the volunteer network, there's also just a ton of kind of marketing and outreach work that we need to do. And Wes and Dave and Arena are doing amazing work here. We want to dramatically ramp up the number of users and jobs per second on the network so that we can test the code so we can make it better, connecting with different language communities and so on. And I've said to Enrico, because Enrico, one of our developers, is also a data scientist, like, you have a red flag, and if you ever feel like the UX is bad, I want you to wave the red flag, and we'll just stop what we're doing and fix it. Because otherwise, we're not going to get the user adoption that we need. And that applies to all of you. Please wave red flags at us on Slack if you try this stuff and it's not nice to use. Then to motivate the work that Kai's been doing a little bit in advance of his talk, we've got these nodes that we're running ourselves, right? It would be great if we could get other people to show up and start adding their nodes to the network. It's a public network. Anyone can participate. Public volunteer network. But why would they do that unless they're just interested? Like, we need to give the service providers some incentives. And we have kind of an idea that we might be able to use FIL Plus as a mechanism to incentivize those service providers to join in before we've done the work on incentives that might, the longer term work on incentives. So I won't steal Kai's thunder on this, but that's what Kai's going to talk about, kind of how we might be able to do that. And there's a really good demo that I'm excited to see. Now, disclaimer, I am in no way an expert on game theory, but this is like starting to talk about the incentive layer work. So I've been learning a bit about game theory, and it's this notion of developing the rules of the game for if there's a strategic community of nodes who are trying to do what's best for them. And there's this nice quote at the start of this Stanford course that I've been reading. There is a well-developed science of rulemaking. It's the field of mechanism design. And the goal in this field is to design rules so that strategic behavior by participants leads to a desirable outcome. And so a good example of this is auctions. And so there's this notion of a dominant strategy, which if there's a dominant strategy in a set of rules, or that kind of falls out of a set of rules, then it's rational for all of the players to play that specific strategy in order to maximize the value to them. And there's another concept called dominant strategy incentive compatible, which basically means that telling the truth is a dominant strategy. And if you've ever looked at how auctions work, it's quite interesting, because if you have a first price auction where, suppose I'm selling my phone to all of you in the room, and you all submit your bids, and then I give the phone to the person who bidded the highest, and they pay me what they bidded, then that actually isn't dominant strategy incentive compatible, because it encourages people to lie about what the phone is really worth to them, and think about what they think the other people in the room think it's worth, and then try and use that information or use assumptions about that information to get the phone for less money than their true value. Turns out, though, a second price auction, which is where everyone submits their bids for my phone, and then I give the phone to the person who gave me the highest bid, but I only charge them the amount that the second highest bidder bidded, is dominant strategy incentive compatible. And that's why that is the auction format that eBay uses. Interesting stuff. We need to make our protocol, our mechanism that we're designing for this network, have similar properties to this. Unfortunately, it's a lot more complicated to have a globally distributed compute network than it is to do auctions. Yeah, I'm excited to have met a game theory expert who I might get you to come and do some talking later, who we can collaborate on this. So I also just wanted to quickly kind of do a sketch of what we currently think in terms of the protocol or the mechanism. So, and there's a Google Doc at the tiny URL at the bottom there. If you scroll down a bit in that doc, then please add comments. It's open to the world. I really want smart people to come and break our protocol now and for the duration of time that we are building it before we deploy it anywhere, so that we make it as good as possible, please. So in this system, we have some requester nodes. Now, you can think of the requester nodes basically as being the clients. They are running on behalf of the end users, and the end user trusts the requester node. And then we have an accounting system, which might be a smart contract, or it might just be a database or whatever, but it's an accounting system with wallet balances. And then we have some compute nodes on the right-hand side. And the requester nodes and the compute nodes, they are open to the entire world, so anyone can show up and anyone can run modified versions of the code that do nefarious things in order to try and maximize the value to those participants. So the rough sketch, and again, this probably has 100 holes in it, please come and tell me what they are, is the following. So all the nodes in the network stake some minimum balance before they get to do anything. And I've drawn these diamonds like on the accounting system, but there's actually one of them per entity in the system, right? There's a wallet balance per requester node and a wallet balance per compute node. And there's like a minimum fee for entry. You can't do anything in the system until you've got this minimum wallet balance. And then a requester node puts out, I guess we're calling them invocation specs now. A requester node puts out an invocation spec or a job spec, a request to be done, for work to be done, and they say, I want one node to do this, please. So concurrency equals 1. And at this point, the requester node doesn't know which of the compute nodes are going to be truthful or not. So one of the nodes bids on the job and has the bid accepted by the requester node. Of course, multiple nodes might bid on the job, but the requester node will only pick one of them because the requester node picks enough bids to satisfy the concurrency. And then the compute node it does the work, hashes the result, and that's why it's important we have deterministic execution so that we can compare the hashes. It encrypts the hash of the result with the requester node's public key, and also the compute node's ID, which is probably the compute node's public key as well, as a salt, so that the other compute nodes can't just copy that result and claim to have done the work, because it's tied to that compute node's identity. And now, notice the number in the hexagon, septagon, I don't know, that one has gone from 1 to 3. So some of the time, with some probability, the requester nodes will some of the time ask for work to be checked. And the compute node doesn't know ahead of time whether the concurrency is going to get bumped up or not for their job. So they're kind of always on their toes. It's a bit like buying a ticket for the train. You're not going to have your ticket checked on the train every single time you ride the train, but as long as you have your ticket checked enough times as a proportion and the punishment for not having a ticket is sufficiently high, then it becomes rational for you to buy a ticket every time you ride the train. So some of the time they get their work checked, and then these other two nodes do the work as well. And that percentage of the time might be like 3% or 5%, so it's small as a proportion of the overall cost of doing the work, which means there isn't much of an overhead in terms of the kind of environmental cost of doing the work versus not having the verification system. Like most of the time, you don't need to check the work. And then the three nodes execute the job, submit the hash as evidence, and then by comparing the hashes, and on the assumption that the work gets evenly spread across the network on average, and that less than a third of the nodes are malicious, then on average, the requester node will be able to assume that if one of the nodes was lying, then you're able to detect that because it's 1 out of 3 that was lying. And then, according to the smart contract running in the accounting system, you can then slash the wallet balance from that node. Now, that's how we're thinking about catching out compute nodes who are lying. What about catching out requester nodes who are lying? Because we don't want requester nodes to show up on the network and screw with the compute nodes. So the compute nodes could correctly compute the result when the requester node could just lie about whether they were truthful or not. So how do we deal with that? The idea is if the compute nodes have all correctly done the work and they're all being good actors, but the requester node says, oh no, you lied, then they can kind of gang up on the requester node just by revealing the encrypted hashes on the chain. And then that would prove to any observer that the hashes did indeed match and the requester node was lying about whether they matched or not. The lying requester node would then be slashed. So there's probably, like I said, 100, 1,000 problems with this protocol. This is just our first pass straw man. So please come and poke holes in this. If there's prior art that we've missed, please let us know. We'd love to collaborate with this with the community. And then, yeah, I've just got a few more words. So how are we planning on testing this mechanism that we're designing? We're going to build a simulator. We're working on this now. It's not going to be a real network instead, but it is going to share as much code as we can with the network code. The idea is just to build massive simulations of these systems, and then the goal is ideally we run the simulator and the kind of bad guys that we've put on the network, we watch their wallet balances go to 0 because the mechanism is working. And then we iterate on trying to build smarter and smarter bad guys to show up on the network and be malicious in other ways. And we're kind of playing war games with ourselves at this point to try and find problems. And what we might also do is have a bug bounty program. So we run this simulator on the internet and invite people to come and show up and try and kind of win the game and maybe pay out bug bounties to people who manage to come up and then share with us what the how they managed to break the protocol. So Simon's going to talk more about this, but in terms of the incentive layer, it matters to us that the work is deterministic. We're going to try and enforce determinism in the compute layer. Big open question is how can we make a deterministic system easy to use? People have lots of existing code. We want them to be able to bring their existing code and mostly run it in a system with no clock, with no dev random, with no threading. And there's probably some things that we can do to make that easier for people. I think Simon, well, I'll let you talk about the clock in your talk. Then we're also going to connect, we're going to prototype the smart contracts that these kinds of systems can use. We're assuming that we're targeting FVM as a place to run the smart contract that we'll write in Solidity or as a Rust actor, etc. We're concerned about the latency challenges, but payment channels could help with that. And another idea that we have is to start with a centralized accounting system, but still have a distributed set of requester and compute nodes trying to mess around with each other, just as a way to parallelize the development of the accounting system and the mechanism. So that's one thought. The goal would, of course, for the whole thing to be decentralized eventually. And then another thing that we're looking at doing, and if there are people who have expertise in this, then please come and talk to me, is looking at formal verification. So formal verification is a way of kind of building a mathematical model of a protocol, and then have a model checker run against the mathematical model to model kind of the most general adversary and compute the set of all possible interactions between the adversary and other participants in the network. I worked on this a little bit at Oxford in 2008, but I think that was quite a long time ago, and I think the world's moved on since then. And so looking at projects like TLA Plus, and there's also some interesting projects listed here that apply specifically to doing formal verification on smart contracts. So I think this is a really exciting research area. It's a research area. It's probably going to take us quite a long time to do this. But my general approach here is like, let's kind of have the mechanism that we're designing in the middle and try and break it in multiple different ways using formal verification, using the simulator, and using game theory. So broadly, that's the approach that we're taking. I'd love it if people have done this before and want to say, do this one more or first, and give us input on that. That would be really helpful. And then the last thing I want to say is there's been a lot of talk about reputation systems. Our current thinking is that we don't need a reputation system in order to implement the mechanism that I described earlier. Notice that there was never any mention of a reputation system in the protocol that I described. However, the outputs of that system that determined that certain nodes were telling the truth or lying about certain jobs could be used to build reputation in an external reputation system as kind of a history of events that could be used as an input to it. There is another way of doing this, which is that we build the whole system around a reputation system. But I don't know, it feels purer to try and do it with staking first. So yeah, we're going to try and bring these things together. We're going to try and create a protocol that will power the world's compute for the next century. And we're going to do it open and collaboratively with you all, hopefully. So yeah, that's the end of this bit. Awesome, thank you.